Hello, Jean-Baptiste Delafage, Andrew Carling, and myself are going to present you in this short video our project for the course CIVL 4320, Introduction to Structural Dynamics. The project will explore the resolution of the monoplane equation for general wings with TI Inspire calculator. Last semester, all three of us followed the lecture named Aerodynamics given by Professor Larry Lee. At some point in the course, we were facing a long and tedious calculation, requiring an iterative process and a lot of focus so as not to make any mistakes. We were convinced this calculation would be much faster and reliable if done with the software. Since we did not have the TI Inspire calculator for the final exam last semester, we wanted to take our revenge on this calculation during the project of this class. When one considers the aerodynamic properties of a wing, the airfoil is not the only thing to consider, since the edges, or tips, of the wing modify significantly the flow, creating counter-rotating vortices at the wing tips, and creates a lot of drag. Geometry of the wing is to be considered as well. For wing geometry, several parameters can be varied. It can be the airfoil, the angle of attack, the chord length, and the wingspan. The airfoil is the shape of the wing when doing a cross-section of it. It directs the flow, and by modifying it, you can modify the flow velocity and therefore the properties of the wing. The angle of attack, usually given by the letter alpha, is the angle to which the airfoil penetrates the airflow. This angle can be different depending on the position of the wing. If the angle of attack is smaller in the wingtip than at the wing root, which is close to the fuselage, then it is called a washout. This angle can therefore be a function of the position along the wing's length, and this is very commonly done on aircraft so as to improve the plane's stability. The airfoil chord length, or usually given by the letter C, is the length of the airfoil or the width of the wing. By varying it, you can vary the wing surface area and so the lift and drag generated by the wing. It is usually not the same along the wingspan. The closer to the fuselage you are, the longer the chord length will be, usually. The wingspan, usually given by the letter B, is the length of the wing distance from tip to tip. The equation used in our case is the monoplane equation. The monoplane equation intervenes in the study of aerodynamic properties of a general shaped wings that has a finite span in the lifting line theory, a theory commonly used that approximates the wing as an infinite number of horseshoe-shaped vortices along the lifting line. This equation enables the calculation of essential coefficients, the AN coefficients, such as and therefore allow us to calculate the lift and drag properties of the wing. This equation depends on the geometry of the wing and is used to study the wings with a general geometry. I will now let Jean-Baptiste explain you more in details about this equation and how to solve it for the case of a tapered wing. As you can see, this is a tapered wing.
So, for our project today, we're gonna try to solve the monoplane equation to find the general lift distribution of airfoil, like this one. So the first idea is to divide the wing in different angle. So we will use pi over 8 as a base, and then 2 times, 3 times, 4 times to divide the space of the wing. So from there, we have the monoplane equation, which is equal to that. So first of all, C is a function of theta is equal to C root minus C t cos theta So C root is 2.4, C type is 1.5. We chose airflow with this kind of parameter. Then we have the lift slope A0 equal to 5.541, and also the angle of 0 degree angle of attack equal to -4036, and the washout equal to 2 degree, which be useful for the angle of attack. So how unknown is the angle of attack? So our study will focus on the angle of attack to see how the angle of attack of the plane will impact on the lift coefficient and the drag coefficient also. So we got this equation. So the idea from there is to divide it in 4 different equations as a function of the angle. First of all, the pi over 8, pi over 4, 3 pi over 8, and pi over 2. So finally we get a system of 4 equations, which are function of an, which is what we are looking for, because it's from this coefficient that we will get the lift coefficient and the drag coefficient. So as we can see, it is very messy and very hard to calculate. So the idea is to put this system as a matrix form. So we will have matrix M, which will multiply the 4 an coefficient, A1, A3, A5, and A7, equal to B, the second part, which is not a function of an. So from there, it will be way more interesting to use a calculator, the TI-CAS calculator, to solve this equation, and then be able to calculate the lift coefficient and the drag coefficient, as you can see, which are a function of A1 for the lift coefficient and the sum of all the an for the drag coefficient.
And so here we re-outline the problem, state all the variables again on the CAS. We put in our equation for the area, as seen here. Move on to the aspect ratio, and this is a crucial part in the CAS. So our function of alpha, we now leave the variable alpha in. So the physical angle of attack of the plane is never defined, something we couldn't do by hand. And so we move on, we continue to define everything as normal. The chord length here, which again varies with the angle that we look at from above, from a bird's eye view of the wing, as Jean-Baptiste said. Again, defining the weight here, the weight, the density of the air, and the airspeed. We then are able to use a CAS to solve the lift coefficient. This isn't a very hard calculation to do by hand, but it's still far more convenient to the CAS doing it. And then this is where we go on to our monoplane equation. And so what we can do with the CAS is set it up in this equation format here, and we can essentially just have it automated. So the idea here would be that we give this file from here on to the students, and then the students don't have to worry about doing everything by hand or reprogramming this. It would be very monotonous and take a long time to do this in an exam, and you don't really prove anything either. The equation would generally be given in a formula sheet, so this would be far more simpler. And so now we can just work by our ij definition, as we've done here. So if we move down with I, we're changing the angle. So I times 2 will give us pi over 4. I times 3, this column, will give us 3 pi over 8, and 4 will give us pi over 2 as we want. And if we move to the right, our j terms will change. So column 1 will give us 1 here, column 2 will give us 3, 5 and 7, exactly what we want. And this is done here exactly. So there's no need to do 16 iterations at all. it's all done automatically for the student. And then we can use the cast to invert this. Again, this would be basically, it would be impossible realistically in any exam to have to take the inverse of a 4x4. And then we can get the right hand side of the monoclinic equation here. And again, we only need to do one variable to change I. So we only need to change I from pi over 8 up to pi over 2. And that can just be done here in this matrix form. You can see here we have all our equations, and the key part again is that we're able to leave the angle of attack in. So we can actually vary this and look to see how the angle of attack affects our lift coefficient and drag coefficient. Moving back to before, we know that our final matrix, as Jean-Baptiste explained, will be the inverse of the left hand side times the right hand side here. And then our equations for the lift coefficient is here. And again, the angle of attack is still there. And for the drag, we use this section here. A little typo there. We use this section here. And then to actually get a nice plot of this, all we have to do is set alpha equal to x, so that's our x-axis. And again, for the lift coefficient. And here we have the most rewarding part of using the TI Inspire. We can actually visualize the trends, which is crucial as an engineer if we're looking to design for a particular need or purpose. And so here we can see the lift coefficient increases far more quickly than the drag coefficient. And so from this graph we could look to pick off a particular point. Note that we cut it off at angles greater than 15 because in practice, well, in practice really above 12 degrees, an angle of 12 degrees, the fundamental theory this is based on, thin aerofoil theory, will begin to fail. That can be seen from other curves as well. But yeah, this is the most rewarding part, and this is what we'd hope students would gain the most from in this application. And so in a similar fashion to the tune mass damper question which we had in our exam, we would give the students this file to store on their calculator. So they don't need to do any of the monotonous typing out of the equations. It would all already be given there for them and explained. And then they would be given the question with all the parameters, and they would need to input the variables and manipulate the equations to get the results required. And then again, comment on the trends, the effectiveness, how they see the aerodynamics changing. With the CAS calculator, we would want to increase the scope of the question. So rather than asking them to just calculate based on simple formulas, which you can do by learning through rote, we would ask them to implement their knowledge and try and visualize the trends, actually give feedback as to manipulating what parameters how that will influence the aircraft performance. And so what we like to do is to apply the TI Inspire to exam type problems. And so this is an exam type problem from the aerodynamics module taught here at HKUST for mechanical engineering students, mechanical and aerospace. And here you can see the question above, over here, with all the variables. And below, as Jean-Baptiste was explaining, here's the monoplane equation. So you see this is really complex. It would require 16 iterations to go through. And what happens in exams is generally the students aren't requested to calculate all of this. They're either given the values straight up, or they can only calculate one or two of them, which isn't really encapsulating the whole thing. And also crucially, there's very little scope with so many variables to actually tinker with the variables, see how the variables influence one another. There's at least 5 variables going on here, so again that'd be really hard for the students to depict and see for themselves.
As a conclusion, one can see that the use of the TI Inspire made the resolution of this equation not only faster, but also more accurate and reliable than if done by hands. With this calculator, different geometries can be studied and therefore allows us to optimize the wing configuration to fit best the flight requirements. It can easily be done by changing the formulas for the angle of attack and the wing shape. With this calculator, we were able to see the evolution of the lift and drag coefficients with the evolution of the wing shape and the angle of attack. Even if the model does not take other factors such as turbulent flow and flow detachment from the airfoil at high angle of attacks, phenomena that increase drag significantly, we can still underline some fundamental properties of the generation of lift and drag by wing. Through this project, we learned a deeper use of TI and Spire and had a deeper insight of the work of engineers.